Alright, so today's episode is brought to you by the letter A, and that would be aliens. Now, do aliens exist? Blah, blah, blah. Who knows, right? Some religions believe it, some don't. Some have incorporated it, some haven't. Some just don't even address the issue. Now, people usually believe that there's something else out there. I mean, if you look at the stars, you can't even see any. Thousands and thousands of them out there. There's gotta be another species that lives out there. There's gotta be. And here's a formula to actually calculate if there is.
The Drake equation attempts to estimate the number of technological civilizations in the Milky Way galaxy, we call that N, with whom we could make contact. And it's usually written as N equals R star multiplied by F sub P multiplied by N sub E multiplied by F sub L multiplied by F sub I multiplied by F sub C, and lastly multiplied by capital L. All those factors multiplied together help to estimate the number of technological civilizations that we might be able to detect right now. Our star is the rate at which stars have been born in the Milky Way galaxy over the last few billion years. So it's a number that is stars per year. Our galaxy is 10 billion years old, and early in its history, stars formed at a different rate. All of the F factors are fractions. Each one must be less than or equal to 1. F sub P is the fraction of stars that have planets. N sub E is the average number of habitable planets in any planetary system. F sub L is the fraction of planets on which life actually begins, and F sub I is the fraction of all those life forms that develop intelligence. F sub C is the fraction of intelligent life that develops a civilization that decides to use some sort of transmitting technology. And finally, L, the longevity factor. On average, how many years do those transmitters continue to operate? Astronomers are now almost able to tell us what the product of the first 3 terms is. We're now finding exoplanets almost everywhere. The fractions dealing with life and intelligence and technological civilizations are ones that many experts ponder, but nobody knows for sure. So far, we only know of one place in the universe where life exists, and that's right here on Earth.
Now, I don't know if you would actually want to try using this formula. I don't even think you can, but it's a way to give you a sense of the possibility that there is a life on other planets.
Scientists, including SETI researchers, often tend to make very crude estimates and acknowledge that there are very large uncertainties in these estimates in order to make progress. We think we know that R star and N sub E are both numbers that are closer to 10 than, say, to 1. And all the F factors are less than 1. Some of them may be much less than 1. But of all these unknowns, the biggest unknown is L. So perhaps the most useful version of the Drake equation is simply to say that N is approximately equal to L. The information in this equation is very clear. Unless L is large, N will be small. But, you can also turn that around. If SETI succeeds in detecting a signal in the near future, after examining only a small portion of the stars in the Milky Way, then we learn that L, on average, must be large. Otherwise, we couldn't have succeeded so easily. A physicist named Philip Morrison summarized this by saying that SETI is the archaeology of the future. By this he meant that because the speed of light is finite, any signals detected from distant technologies will be telling us about their past by the time they reach us. But because L must be large for a successful detection, we also learn about our future, particularly that we can have a long future. We've developed technologies that can send signals into space and humans to the moon. But we've also developed technologies that can destroy the environment, that can wage war with weapons and biological terrorism. In the future, will our technology help stabilize our planet and our population,